by way of introduction, Bruce Eglington is going to speak next, and Bruce is a research partner here at Metal Earth at University of Saskatchewan, and we have been co-funding a postdoctoral fellow, Sherry Armistead, between Bruce's group and the GSC at Metal Earth. And Sherry's not available today, so Bruce is going to give us an update on her work. Thank you very much. Go ahead, Bruce.
Yep, and Sherry unfortunately is down in Tasmania now, but she was also presenting an invited speech at GAC, which happened to coincide with this session. We've been working for some while being interested in the relationship between endowment and the isotope signatures, anything that indicates something about the process that's involved. So if we just look at the endowment aspect first off, plotting up gold-related deposits on the left and base metal, essentially VMS deposits on the right, showing the actual contained metal content as best we can derive it from available databases at this moment, relative to supercontinent cyclicity and metamorphic ages, which effectively capture the time periods when the major amalgamation of these blocks occurred. One sees that the various deposits, both VMS and orogenic gold, are fairly closely tied to the amalgamation phases, and they're very variable endowment between some of these major blocks. So from an isotopic perspective, a lot of work's been done in Australia. It's obviously, a lot of it has also then been transferred here, and Metal Earth is doing some fundamental work with this. But in all cases with these evaluation tools, it's best if we have multiple systems to work with. Obviously, neodymium, hafnium, and lead are some of the primary ones. As you've just seen, one also incorporating chemistry, oxygen isotopes, etc. In general, lead isotopes are more sensitive to crustal involvement, and that's one of the reasons we're keen to involve it. But at the same time, some of the previous studies have suggested that low model source mu values might relate to endowment. A couple of slides relating to lead isotopes, just to set the scene. We're going to calculate everything relative to the Stacey and Kramer's model. It's just a convenient one that works well with ores, and as an average that works well around the world. But besides the average value, one can actually calculate these uranium-lead ratios that would appear in the source region with low mu values, that's the uranium-lead ratio, relating to areas where you have less enrichment in uranium, and up into higher mu values where you have more. That will typically relate to things like the upper crust being enriched in uranium and hence having over a long period of time higher uranium lead, whereas the mantle is lower. And if you've had an ancient uranium loss event, then you can produce a very depleted lower crust. It's important to realize that if you have, in this case, two different sets of samples illustrated by the subhorizontal purple lines, depending on where those project back in terms of their present day uranium lead, they define what the model source region would have been. The top one obviously dials back and implies a very upper crustal type high mu environment as the source region, whereas this bottom one implies a very much lower in source region, a low mu environment. And that's the essential aspect of playing the games with lead isotopes. It's relatively difficult to work with that particular way of plotting things and seeing how things have changed through time, because it's all on curves. So we've transformed from that lead isotope plot into an age versus model source mu plot, and then just emphasize the high mu settings in browns and the low mu settings in green relative to the more typical origin type well-mixed environments. There are multiple low mu occurrences through time, just highlighting a number of the more important ones here, of which the superior is one of the most important and certainly by far the best studied, and hence our interest and involvement in metal earth. At the same time, we can have a look at when these low mu occurrences occur and bring back in some of that metal endowment, here shown for gold in yellow and the VMS-related base metals in blue. And you'll see that many of these low mu occurrences seem to be coincident with some of the high endowment episodes. We can show that distribution of low versus high mu on a general geological map of the world, which just allows us to focus on a few of the regions. Taking Pilbara and Yilgarn as an example, and just coloring in from low to high with this color scheme, you can see that within these, there are very distinct provincialities. As with some of the other high mu areas, we find that the example on the left with the Pilbara stratigraphic succession, that where we get high mu values, that generally relates to the presence of much older felsic crust, which in one way or another has been incorporated in the mineralization process. So that's Pilbara and Yilgarn. Jump across to Zimbabwe and Karpal, very much the same type of thing, very distinct provinciality. Zimbabwe and the ancient gneiss complex in the Barberton region shows the higher mu signature, whereas some of the slightly younger Murchison domain, etc., shows lower mu. The slave, Craton, very much the same type of thing, just quite distinct distinction between west and east slave. And again, the west slave, which is where Acasta is the one that has the old felsic crust available, as well as cover sequences, which again provide evidence that there is an older buoyant substrate. And then moving here into Superior, with the available lead isotope data out of deposits, very distinctly dominated by low mu, with a few occurrences of higher mu in the data that is available. In terms of the spatial associations and looking at some of the supercontinent cyclicity side of things or associations, there does seem to be a relationship between some of the pre-2.7 or roughly 2.7 billion year old continental associations, with some of them having generally low mu and other associations generally high mu. Once again, though, the ones that show the high mu in any of these plots effectively require the influence of older, which is typically upper continental crust. Coming back in to focus on Superior again, if we look at the stratigraphic succession and variation of the deposit sulphide data, it's a relatively limited data set. There is an apparent slight increase in mu as one progresses up succession. We can bring in whole rock data, although it's more scattered and less trustworthy in the sense that one has to extrapolate from higher because of higher uranium lead ratios, but the general pattern is similar. In this case, we're also introducing data outside of Abitibi, so this is for all of Superior, but just using the vertical bands which relate to the actual timing of the stratigraphic succession within the Abitibi area to help set the scene. It's interesting to have a look at some of the other terranes within Superior where we know that there is older crust present. Taking the Uchi terrane, for instance, here we've got two sets of data. It comes out of various greenstone belts. And if one looks at the more western section there, the ones that are slightly yellow, slightly more elevated in mu content, those relate to areas where one has platform successions, evidence for older upper continental type crust. But interestingly, even though one has that, one doesn't see extensive evidence for the influence of that older crust. West Wabigoon is also a relatively complex area with variable ages of protolith. Many of the deposits here are also generally low mu. Martel have suggested that this is a fairly allochthonous terrane, and possibly that is one of the reasons that we're seeing the generally low mu it's not seeing the influence of the underlying Winnipeg River material, but that was all introduced at younger stages. So we're seeing a predominantly mafic, relatively juvenile area. Again, coming back into this as a reminder of the positions we're in, wanting to have a look at the variations relative to other data that has been published, made available, and a lot of which has been derived through Metal Earth projects. One of the things we've noticed with the lead isotope data is that there are distinct east-west trends in the data. I'm only showing here the lead sulphide data again, but even the whole rock data shows the same type of thing. And that seems to be contrary to the contoured trends for hafnium isotopes, for instance. They're expressed as epsilon hafnium values. So this had us worried a bit, and we delved into trying to understand why this might be, as well as looking at ways to produce diagrams when it comes to maps. People are very tempted to plot up epsilon values and color according to those epsilon values. But the point I want to make here is that if you had two groups of rocks, the blue line trend in the top left and the top right, or the red line trend, those effectively are both being derived and reworking particular ages of rocks, where the blue one is distinctly younger than the red one. If we use epsilon, color according to epsilon, symbolized by epsilon, then those two yellow symbols would end up with the same color, and one sees some of the scatter one sees in the general Australian data. Whereas if we plot T2DMs, we tend to see through this. We can still go into it in more detail and look for localized variations, but the general patterns are far more consistent with what is really being reworked versus what is more juvenile. So we've applied that into the data that David Moll published, and now plotting it up also just as symbols. And effectively, blues here are the juvenile, what would be the more positive epsilon values, if we were looking at it in epsilon terms. The reds would be the more evolved, older, more felsic crust present. And we see much the same trends that we were seeing in the lead isotope data. So we feel that it's generally better to plot the data points because it also looks as though some of the data distribution is influencing some of the contouring that one's ended up having because of the packages that we use and the way those are set up to work. So let's move on and have a look at what are the geological settings that could produce these low mus. Well, one is obviously ancient granulite facies metamorphism, drives off the uranium, lowers the uranium-lead ratio, and it needs to happen a long time before the actual eruption of the igneous rocks, typically in the region of 500 million years. There are reports, or a fair number of reports, of fairly low uranium-lead ratios in mantle xenoliths, quite a number of these from various places around the world, so it's certainly feasible. Many of these are argued to be melts, not subsequent alteration. And we do know that low model source mu magmas are still evident in the oceanic domain today, as illustrated with locality-wise with these couple of diagrams at the bottom. We can incorporate older crust into mantle sources by a variety of processes. The best known of that in the modern sense is the Dupole anomaly, and just illustrating for one part in the South Atlantic. But ultimately, one needs to decide whether one produces a low mu source far back in time and then taps it at subsequent times, or is there a regional process that produces the same type of environment episodically and allows one to tap it? Another thing that has come up with some of the studies is the influence of mantle's oceanic spreading rates might influence the values one gets based on what parts of juvenile or residual mantle get introduced into the pool that goes to produce the volcanics and igneous rocks that we're interested in. One of the interesting things here is the timing that we're talking of. typically around 500 million years. And that strikes us as being quite surprisingly similar to a supercontinent cyclicity. So we just wanted to investigate that possibility. What might the influence of that be on producing an episodically produced unusual environment, which is juvenile with respect to neodymium and hafnium, but is ultra depleted with respect to uranium-lead ratios. So if I just look at where these low mu excursions are and have a look at some of the high endowment episodes in the Southwest Pacific, if that was actually, if the mantle source that's producing the high endowments is something that was effectively isolated about 500 million years ago during formation of Gondwana, the Taconic and the Central Asian orogenic belts effectively could relate back to things that were happening either during Rodinia or more particularly during the Arabo-Nubian phase of subduction. If we look at stuff related to some of the Grenville, there is nothing there, and possibly that's because 500 million years before was effectively during one of the Mesoproterozoic lulls. The Trans-Hudson has a fair amount, but not as much as some of the other lunar-related ones. And again, maybe it's related to when the mantle was up, the mantle that went into producing the mineralization was isolated. Then Birimian, we write back to the typical Superior 2.7 billion year period for mantle isolation related to a major crust, felsic crust extraction event. And if we go back to Abitibi and the Superior, just maybe we can relate it to the lithospheric bloom, in which one produced a lot of what is now vanished felsic crust. And it also coincides with when the first eclogite intrusions are found in diamonds. Possibly we're seeing something of a process that helps us understand why we get these increased enhanced endowments in certain periods and not in others. So conclusion-wise, the Superior has low model source mu, which contrasts with the mantle-like neodymium and hafnium, and one can explain that through an episodic event, but it does require a lead source, which has the lead indicates that whatever source one's working with must have evolved for several hundreds of millions of years, even though the neodymium and hafnium data don't provide that evidence. We see similar variations in several other well-endowed global districts, and we would suggest that there might be a common process which could have metallogenic implications, which we should be considering for exploration. And I leave it at that point. If there are any questions, thank you.